started. And today we're going to be keep talking about topics in quantum optics. And in particular, we're going to finish deriving the dipole Hamiltonian under the dipole approximation that we left from last time. And then we're going to go ahead and quantize this Hamiltonian by quantizing the field part and introducing the rotating wave approximation, which you've already seen, I think, before. But this time, maybe this will make more intuitive sense to you. And now, next, after doing the quantization, and by considering the atom coupled to a single mode field, we arrive at the James-Cummings Hamiltonian. And then I'm going to briefly introduce the interaction picture before we actually solve this Hamiltonian. Okay, so that's the agenda for today. But before that, I'd like to clarify something I said last time, which was about maybe it wasn't very clear. Last time I said for the atom, something called the Rydberg atom. Now, a Rydberg atom is an atom with a very large N. So we didn't talk about this, but it turns out these, when you solve the hydrogen problem, maybe some of you know this if you had a course in quantum mechanics before. If you solve the hydrogen problem, you get these N, L, and M states. Okay, and in the simple picture, only the number N is related to the energy. Okay? And it's related to the energy as the energy of the N states. Now, since the hydrogen atom has a bunch of bond states, okay, so the energy is negative, and we're taking infinity to be the reference of the zero of energy. So it turns out that the spectrum looks like this. Okay, so 13.6 electron volts divided by n squared. Now, what does the L mean? The L is indication of the angular momentum, and so L plus 1. Maybe there's an h bar squared here. And this is like angular momentum squared. Okay, and something like that. And the range of L and N, the values is that so for N equal to say N can be any integer. Okay. N is and it's a positive integer. Okay, so M plus are the natural numbers, I guess. And then L can range from 0 to N, okay, to N minus 1 actually. L ranges, okay, so L is greater than equal to 0, less than N. And also L is a integer value. Okay, and let's not worry about M for now. Okay. So now what this allows us to do is, when N is extremely large, okay, and in the simple model, all the L states are degenerate. Okay, so as I said, since the energy is only related to N, all the L states are degenerate. So if the atom was at a very high N state, okay, state with high N, okay, it turns out that at a very high N state, say in the typical quantum optics experiments, they use the N equals to 50 this state. So your L can go from 0 to 49. And we know that, remember from our angular momentum lectures, these L's, they signal the spherical harmonics, right? And the spherical harmonics are complete. Okay, they are complete ranges. And if I sum enough of them, I can expand a very localized function, angular, right? If I had a function that's, let's say this was the core of the atom, or the nucleus is. Okay, and this was the rough atomic orbit. Okay, if I wanted to expand the packet over here, I would need to do so for it to be localized to a certain degree. I would need to do so by summing up over a large number of L, a large number of spherical harmonics. And this is only possible if I am at extremely high N, right? Like N equals to 50. So going from, and so a state at N equals to 50, about 50 can be well localized angularly. by the fact that I can sum over all the generated L states, right? Okay. So it is possible to localize the electron, right? But then you need to think about, well, the electron, when it's localized, it's still going to evolve in time, right? And as it evolves in time, there's a characteristic time to this motion. And whenever there's a characteristic time, we fix the uncertainty on the period. Right? When we fix the uncertainty on the period, we introduce some uncertainty in the energy, which means that maybe not only the n is around 50 is contributing, but also the maybe n equals to 51 and n equals to 49. Right? And we need to sum over all of these states. What's going to happen is when you sum over all of these states and you think about time evolution, then the wave packet is moving with different frequencies. And we know that when we have a wave packet composed of different frequency components, it's going to evolve with the group velocity. Right? And the group velocity is roughly, in the case of a wave, right? We know that the group velocity, the group, is roughly d omega dk, right? The analog in this case is basically the frequency difference between the adjacent. But this is just, if you think about this as a differencing formula instead of a differentiating formula, then it's just the group velocity would just be the difference between the time evolution of the 50th and 51 state, for instance, right? So then we get that the angular velocity, okay, which is omega of rotation, let's call it omega rotation. This is roughly over the divided by h bar, because we need to turn the energy of the n state into kind of a frequency, right? So this is what I mean. So for a Rydberg atom, at extremely high n, for a very excited atom, we can have, roughly speaking, the electron cloud is going to look like a well-localized packet that orbits around the nucleus at this angular frequency. Right? And notice that this frequency is, we know that this is the En scales as 1 over n squared, right? So this differentiation gives you like 1 over n cubed. And this is approximately equal to 1 to the transition frequency between the 50 and 51st states, right? Because essentially we're just doing a differencing in the frequency. So that analogy that I made in the previous lecture is not just a guess. This actually happens, and this is where, so for a highly excited atom, the atom can actually look like an electron cloud orbiting the nucleus. It can actually look like that. Okay, so that was a point I wanted to clarify. All right. So and then when you have this, the atom essentially is a point charge. And roughly a point charge. Okay, so the electron is almost localized over here. So the atom is essentially a dipole, right? Dipole of r, which is basically the expectation value of the electron radius orbit of the radius of the electron orbit. So the atomic dipole is basically atomic. Is something like this, rotating with angular frequency, which is equal to this, which happens to be the transition frequency. Okay. And this will show up later in our discussion. But qualitatively, this is what's happening. Okay. And actually, when people first thought about the atom, this is where they started. But they found some problems with this. But Niels Bohr was able to bridge this picture. This is for the very highly excited atom. He was able to bridge this with the less excited atoms in the old quantum physics. But anyways, we move on from here. Okay? And as I was saying, this orbit, okay, we derived from last time, the radius of this orbit scales as n squared. right? And so the radius, okay, is on the order of n squared times the Bohr radius. The Bohr radius is 0.5 angstroms. And when we're using n of, say, 50, right, then the atom is actually about 100 nanometers big. So atom can be very big. And in fact, if you go up to n equals to 100 or so, which can be prepared experimentally, then the atom is as big as a virus, on the order of microns. Okay, so if you're interested in this, you can read up on Rydberg atoms. Maybe for your project or something, you can read up on Rydberg atoms. Okay, so now, okay, but then this we see that this transition frequency scales as n cubed. So the frequency, we're always in the, which means that the wavelength scales as n cubed, right? So we're always in the regime. If we're doing this near transition kind of physics, then we're always in the regime where the wavelength of the field is much greater than the size of the atom. This is what allowed us to do the dipole approximation. So previously we wrote down the Hamiltonian. The classical Hamiltonian looks like this. Square? Oh, yeah, square outside. And then I've already told you that we're going to be working in the radiation gauge, in which the U doesn't appear. So there could be a binding potential for the electrons. So last time we said that we're going to approximate A by virtue of this dipole approximation. We're going to approximate A as just the value of A at the position of the nucleus. Okay. So roughly speaking, the field is going to look constant across the atom. Okay. Once we've done that, then we can go ahead and write. I just basically replace this A with R naught here. So now this is the problem is greatly simplified because if I were to turn to quantum mechanics, right, I know that P gets replaced by what? H over I, the nabla operator, right? So, and there is a squared here. So if I were to expand this thing, I would get terms where things will depend on the divergence of A. Right? And basically, right now by replacing A with a constant R naught, okay? But keeping its time dependence, I basically thrown away those parts. Right? So things are really simplified in this way. Okay. So if I was to go to quantum mechanics, okay, I write a Hamiltonian becomes an operator, right? Okay, and P becomes the operator that we're familiar with. Now A is just a function, right, at this moment, right? Because we haven't quantized A, so it remains just a function. And then V is an operator, but we know that it's just a function of the operator R. Right? So let me indicate that it's an operator. Okay. So if we proceeded directly to quantum mechanics, this is what we would do. But before we did that, let's think about this Hamiltonian here. Okay. Let's contrast it to a Hamiltonian describing a particle that's not coupled to a field. You would just not have this part here, right? Otherwise, it's the same. Because that Hamiltonian, which I would call the atom by itself, right? This is given by what? G squared, right? Plus V of R, right? Which describes the electron in the atom by itself. Right? So notice that what's changed over here is, by coupling to the field, we've essentially changed the momentum of the atom, right? We've added a factor to its momentum. Okay? And if you think about Fourier transform, what happens when you have a shift in the momentum? A shift in momentum state. A shift in frequency gives you a phase factor in time domain, right? So a shift in momentum space gives you a phase factor in just coordinate space. Right? So we expect, and what's the sign here? If I have a subtract, okay, I need a frequency shift the other way. Right? Because think about this. If I wrote down the inverse Fourier transform for you, right, dk into the I kx right? And if I were to subtract something from k, right, and if I subtracted something from k, I can subtract something here, and by multiplying a positive space factor out. Right? I'm saying that is equal to e to the I k naught x. Multiplying this, I subtracted it on the inside. To the I k minus k naught. F of k minus k naught. So now this is just the Fourier transform of f of k minus k naught, right? So we get that by subtracting in the momentum space, we basically multiply this factor, right? So we say that f of x gets taken to f of x e to the I not the left, right? Okay. So essentially that's what's happening here, and that's what we expect to find in the solution. So this motivates us to think that if I had some function that obeyed that was the solution of this Hamiltonian in quantum mechanics, which I want to know by phi of x. If I had such a and of course, because there's time dependence here in the Hamiltonian, we know that the eigenfunction would depend on time as well. Okay. So if I had such an eigenfunction corresponding to this Hamiltonian, then I would expect that just by adding a phase factor to it, I will get a Hamiltonian where I will get an eigenfunction that satisfies this Hamiltonian. So the phase factor, according to this, would just be e to the I, e over h bar radio dotted with let me use R. Okay, correct. Okay. So this is essentially what's called a gauge transformation in the sense of Schrodinger equation. So gauge transformation in this case is just a phase shift. And if you think more about this analogy, what's happening when we subtract a momentum from in the momentum space, we're essentially saying we're switching a reference frame. We're switching to a reference frame where we are moving at a velocity of k naught against the actual thing. So you can think about this as being, well, there's a mattress, which is the electromagnetic field, and the mattress is moving, and the atom is moving when it's coupled to the mattress. It's actually moving with the mattress. So now we want to look at things in the atom's own frame, and what you do is you subtract the movement of the mattress, and typically the movement of the mattress will be coupled to the mass, but this is the electromagnetic field, so it's coupled to the charge. This is essentially what's going on. We're just switching a reference frame and you get this phase factor. So in the other reference frame, okay. So let's plot this solution into the original Hamiltonian, okay, and see what happens. Okay. So the Hamiltonian being just this. So now, if I write down the Schrodinger equation, it would be that IH bar d dt of, let me call this, let me call a new solution psi of R t is equal to H of psi of R t. Oh, wait. I made a mistake. I mean, by attaching this phase factor, okay, we've taken this solution and put it into this Hamiltonian. So now, if I define psi of R t equal to e to the times psi of R t, right? Then this wave function is going to satisfy this Hamiltonian. Right. Because I've shifted in the momentum, so I need to attach this phase factor. So I will from here. Okay. So now our task basically is to plot this. Okay, plot the Hamiltonian into here. Right. And that's a bit laborious. So let me do it starting over here. Okay. This is the definition. So on this side, okay, we have the time derivative. Okay, so let me write IH bar. Okay. And let me repeat that. And remember, A is just a function of time, okay? Because we fixed the position to be at R0. Okay? So now if I take the and then so now if I take the time derivative, I get two terms. Right? I get a term where I will take the time derivative of A, and then I get a term where I would normally take the time derivative of the wave function. So IH bar, and it's I equals H bar R dot E. This is one term, and then I just simply multiply this term. Right? I'm going to take this phase factor, which remains after the differentiation outside. Okay. And then I will get another term, which is just the time derivative of this thing. So plus d phi dt. And then I get the phase factor out. Correct? Okay. So this is the left-hand side. And the right-hand side is a bit more tedious. Okay. We can imagine what happens with this potential term. The potential term just sees this, and this just gets attached as a phase factor. So it can be factored out easily. And later, after the factorization, we're going to cancel the overall phase factor anyway. So let's not worry about the potential term. Okay. We need to worry about this term. Okay. So let me expand this. This expands it to what? H bar over I minus H bar over I. Expand it to this, right? So we can interpret this as the gradient, and but you need the divergence here, because normally in the Schrodinger equation you get the equation. Right? So now this thing is going to operate on side of R and T. Right? Now let's think about how many terms we would have. So these differential operators, they're only going to operate on side of R. Right? right? Okay. And then everything else is just multiplicative because A has no R dependence. Because I've already replaced it with R naught under the approximation. R naught is not dependent on R.
A doesn't have an R, but it's.
Yeah, so I'm saying the differentiation is only going to work on these fees.
Because an exponential.
Oh, I'm sorry. yes, they're going to work on this. Right, so, and actually, they're going to work on this, but if you think about it, once they work on this, I get a term out, right? H bar over I, okay. That cancels I over H bar, right? And the EA, okay, E times A with a plus sign is going to cancel these things. Right? And that's exactly how we simplify the problem by doing a phase shift. So instead of carrying out the algebra, let me write down the answer for you. It's not very important. Everybody can do this algebra and find that you will agree with me. So essentially you get this for the left-hand side. And then on the right-hand side, by virtue of this phase shift, we basically just get the original Hamiltonian, which I denote as H original. Okay. This Hamiltonian is for this. Okay. So when this Hamiltonian with the shifted momentum acts on this wave function with the shifted with the phase factor, it's going to be the same as the original Hamiltonian acting on the wave function that's not shifted. Right? So you can simply just write this down. Okay. Alteration of phi of R. And if you don't believe me, you can simply carry out the algebra. Okay. So what we get is that, okay, and then okay, the phase factor just gets attached. Okay, so now let me cancel this phase factor. Okay. And then let's extract the original Schrodinger equation, which consists of this part, right? I h bar d phi dt, and then on the right hand side we have this. This will constitute the original Schrodinger equation. But you see that now we have a new term, right? A new term that is dependent on the time derivative of A. And what's the time derivative of the vector potential? Okay. Under our current gauge, it will be the electric field, right? Okay. So maybe I need to refresh your memory on this. So the electric field, this is equal to minus dA dt. And it's also going to depend on U. Okay? There's going to be a gradient of U somewhere, but in this gauge we've chosen U to be 0. So the electric field is just this. So let's go ahead and replace that in there. You see that, well, by doing this gauge change, okay, this gauge change, what we found is that basically coupling to the field amounts to the original wave function, seeing an extra term in the potential. An extra term in the potential that's proportional to R dot E. Okay. So let me write that down for you. Okay. So we get that IH bar dt, this being the left hand side. Take that over here. Okay. We have minus and then you see that this what you see is there's a minus sign here. If I plug it in, there's a minus sign. But then there are I and I. Okay, so that's another minus sign. So that's a plus sign. Okay. So on this side is a plus sign. I take it over here is going to be a minus sign. R dot E. Okay. And the whole thing operating on this original wave function. Okay. So this is the dipole coupling component. this is essentially what we have said qualitatively. By doing the long wavelength approximation, we can think about the atom as basically a dipole with a characteristic frequency that's rotating angularly like this. Okay, and this is what we find here. Okay, so that's the dipole coupling Hamiltonian, and this part is done. So we move on to the next part, and now you notice that over here, everything about the atom has been quantized. Right? All these R's you should interpret as operators now. Right? These are all operators. Okay. But then the electric field, which is the field part, this is still just a function of R, just a function of space and time. Okay. But now we know that for free space, we know how to quantize the field. So let's think about an atom sitting in a free space coupled to the electromagnetic field. And I can replace this part simply by its quantized version. And that's how we're going to quantize the So let me start over here. Are there any questions so far? Yue, did you want to ask something?
I don't know whether I missed something, but I just feel like for that part, I can cancel the original Hamiltonian. Also, from the left-hand side, cancel IH bar partial phi partial g. So it seems like to me, this gives me the dipole, the perturbing Hamiltonian is 0. Is that correct, or I missed something?
Let me think about it. Yeah, I get what you're saying. You're saying that according to the original Schrödinger equation, this phi of RT should satisfy this Hamiltonian this Schrödinger equation, right?
Yeah.
But maybe I said that too loosely.
Okay, so
Under this gauge transformation, it doesn't satisfy the original one anymore. I'm just saying that this operating on this is equivalent to the original Hamiltonian operating on just this.
So there's no base term.
The original Hamiltonian doesn't have an A in it anymore.
Yeah.
So can the IH bar partial phi partial t, that's
It's not equal to the original Hamiltonian on top of this.
okay.
Yeah. If that's what you're asking.
Yeah, I think another way to see it more properly is to see that the psi that you find in the last line is an eigenfunction of the composite operator, the del minus EA part.
Yeah.
And then if you let that operate on that, you get only the delta left on the right hand side. I think can explain what I mean by this. Say if you have this function, you operate with this operator, say h bar over I del minus EA. Okay, let this operate on this. Then there will be some cancellations going on, and then you will just have h bar over I del psi, and then there's something. So you can think of this thing being an eigenvector, eigenfunction of that. So it just becomes that, and then that's why you get the original back when you do a back substitution.
Right. So essentially, the new Hamiltonian operating on this is the same as the original Hamiltonian operating on this. Well, I guess you need to attach the phrase. Just do the mathematics. Okay, how about this one? Okay. But that's what I mean, because what I said before about this shift in the momentum giving you a phase factor, that's equivalent to if you were to do the mathematics. Okay, so now, starting from here, are there any other questions? If not, then we go ahead and quantize that thing. So let me remind you, so we turn the electric field into its quantized version by doing, so the electric field at R0. Okay. So I can expand the electric field first into sum of different wave numbers. Okay. And then there's a factor corresponding to its polarization. Okay, so let me indicate that this is polarization. And then there will be a factor that's like this. H bar omega k divided by 2 times big omega. And let me tell you what these are. That's what not you know what this is. This is a permittivity of free space. This is the quantization volume. Yeah, I think that's right.
ME.
ME? Okay. Okay. So what do I mean? There's a discrete sum over the wave numbers here. So we're not in a continuum. We're actually in some very large space. Okay. And you're assuming that the field satisfies either periodic or hard wall boundary condition on these things. Okay. So this is the quantization volume, and inside of this volume there are these k, these modes with wave number k. Okay. So now there's something nice here. How do you remember this factor? And you say, okay, you look at the lecture note and you just remember it for life. That's not true. Okay? It's actually very intuitive. You can think about this. Okay? You can think about giving the vacuum energy 1/2 h bar omega k. Okay. And just spreading this across the volume,